Good afternoon, everyone. I'm Jian from Singapore. I will give a talk about the project of repeat buyer prediction for e-commerce. The project is a collaboration among A*, GE, and DBS. There are big sales promotions. For example, in the US, Black Friday. In China, Double 11, which is November 11. The sales promotion is to attract new customers. However, most such new customers are one-time dealer. After the sales promotion, they do not come back to the merchants and repurchase items. Our task is to predict who will buy items again after the sales promotion. Our project is based on a competition organized by Alibaba Group. Our data is the sales records on November 11 or Double 11 at Tmall. Tmall is an e-commerce platform of Alibaba. We are the champion at the first stage of the competition out of 753 teams. Our winning solution consists of comprehensive feature engineering and extensive model training. Alibaba gives us 4 data sets. The first one is training data. It consists of 3 columns: user ID, merchant ID, and label. For every pair of user ID and merchant ID, the first purchase of the user from the merchant is on November 11 or Double 11. The class label is 1 if the user repurchase items from the merchant within 6 months after the sales promotion, that is November 11. We also have some demographic data. The data is fairly simple, only include the age range and the gender. We also have the user activity log 6 months before Double 11. It consists of user ID, merchant ID, item ID, the category of the item, and the brand of item. There's also action type. The action can be click, add into cart, purchase, or add into favorite. It records the user's action on the item. There's also a timestamp. The first 2 digits gives the month, and the last 2 gives the day. The training data has the user ID and merchant ID, which have the same meaning as the user ID and the merchant ID in training data. Our task is to predict the class label in the testing data. In both training and testing data, only around 6% are positive cases. The remaining 93 are negative cases. These are the one-time dealers. Altogether, we have generated more than 1,300 features. For our clear presentation, we organized these features by profiles: user profile, brand profile, category profile, merchant profile, item profile. There are also interactions between profiles, such as the interaction between user profile and the brand, the interaction between user and merchant. The table is the overview of the features. The first row gives one way of organizing the features. That is the profiles and their interactions. The first column is another way of dividing the features. They include count features, aggregate features, recent activity, complex features, and features relevant to age and gender. The 2 ways of organizing features have overlap, and if there's overlap, we tick it. let's consider the column of user and the row of monthly aggregator. There's a tickle. That is to say, we have generated monthly aggregation features for user. In the following, I will give some examples of features. The first one is basic feature. We can generate, for example, the click. We can count the number of clicks of a user in each month from May to November. We can also count the purchase in each month. And we can also compute the click ratio. Let's consider June. In June, there's 1 click, 1 purchase, and 0 add to favorite. Therefore, the click ratio is 1 over 2 equal to 0.5. Product diversity features. We have an intuition, that is, if a user is interested in more diverse items of merchant, then it is more likely that the user will come back to the merchant and rebuy items. The lower left figure gives an example to confirm our intuition. The x-axis is the number of unique items purchased by a user from a merchant. We discretize the value into 4 bins. The green bars shows the percentage of positive cases in each bin. We can see that the green bars are clearly increasing. Therefore, it confirms our intuition. More items, more likely to rebuy items. Penetration feature. We define the penetration of an item as the number of users who have purchased the item in a given period. A large customer base usually indicates that a merchant has a good reputation. Therefore, users are more likely to come back and purchase items from the merchant. User aggregation features. We define by day number. It is the number of the days of a user visiting a merchant. A merchant may have many users. We can compute the by day number for each user. Then we can do an aggregation, for example, average over all the users. If the average value is higher, then our intuition is that the users are more likely to rebuy items from the merchant. The figures on these slides confirmed our expectation. Because of time limitation, I just skip it. Listener activity. We define a ratio. The ratio is equal to the number of items purchased by a user on Double 11 divided by the total number of items purchased by the user. If the ratio is higher, then it is more likely that the user is a one-time dealer. Complex feature. We generated a trend by, for example, by counting the number of purchases of a user in each month. They are the 6 months before Double 11, and Y1, Y2, Y3, to Y6. Y7 is the number of the purchases on Double 11. By these 7 values, then we can compute the slope. We can also compute the deviation of the last month from the previous 6 months. Repeat buyer. If the ratio of for a merchant, if the ratio of repeat buyer is higher, then more likely users would come back to the merchant for repurchase. Market share feature. It measures the importance of brand categories to merchant, or the importance of merchant to brand or category. Use a merchant similarity feature. Let's consider an example with a merchant and 5 brands. The first factor gives the market share of the merchant on these 5 brands. The second factor gives the number of the items on these 5 brands purchased by a user. Then we do an inner product of the 2 factors, and the product score is the similarity between the user and the merchant. We expect that if the similarity is high, then the probability of rebuy is also high. The figure on the bottom confirms our expectation. PCA feature. We use some matrix to measure the similarity of merchants. In the dataset altogether, there are around 5,000 merchants. The similarity matrix is 5,000 times 5,000. It is fairly sparse. To reduce the dimensionality, we apply PCA on the matrix and only keep the top 10 principal components as the features. We have also generated LDA features. We model a user as a document and the merchants as words. If a user purchases items from the merchant, then the merchant is a word of the document. We set the number of topics to be 40. We have also generated features relevant to age and gender. This is based on some observations. For example, clothes and cosmetics are more attractive to women, while electrical devices are more appealing to men. We know that people in different age range have different preference of purchase. Therefore, we have also generated some features relevant to age range. After we generate all the features, then we join all of them together based on user ID and merchant ID, and we get a fairly big table with more than 1,300 columns and more than 2 million rows. We train models on the big tables. We applied quite a few machine learning models. They include factorization machine, logistic regression, random forest, GBM, and XGBoost. The top figure, the bottom of the top figure, we give the performance of the models. We use the AUC as the evaluation matrix. It turns out XGBoost gives the best performance. With the output of single models, we also train an ensemble model, which is a linear combination of the outputs of single models. We call it a blending model. The blending model has the best performance with the AUC close to 0.7. The score is close to the AUC score of XGBoost. The importance of feature groups. Altogether, we have generated 1,364 features. For better illustration, we organize the features into profiles, and the interaction of profiles. We evaluate the importance of each profile. Let's first consider the The first blue bar. We use only the features in merchant profile to train model XGBoost. And by 5-fold cross-validation, the AUC score is close to 0.65. If we use all the features in brand profile, then the AUC score is also close to 0.65. We sorted all these profiles in the descending order of their AUC scores. It turns out merchant profile is most important, seconded by brand profile, and the features of interaction between user and the brand, and between user and category has the least importance. We evaluate the importance of a profile in an alternative way. Let's consider the first green bar. We include all the features except features in merchant profile to train XGBoost and use 5-fold cross-validation. The AUC score is close to 0.7. For second green bar, if we use all the features except for brand profile, then the AUC score is also close to 0.7. Actually, by looking at all the green bars, it turns out all of them are almost of the same height. That is to say, if we remove any profile from the total set of features, then the performance of the model would not drop clearly. By such observation, we draw a conclusion that is, any profile is not a strong indicator of the class level. This is the last slide summarizing our project. We have generated a large number of features to capture the preference and the behaviors of users, the characteristics of merchants, brands, categories, items, and their interactions. Our generated features are useful not only for repeat buyer prediction, they can also be used in other e-commerce applications, such as customer segmentation, product recommendation, and customer-based augmentation for brands. It is a very tedious task to generate and manage so big a number of features manually. So one future work in our agenda is to automate, at least partially automate the feature generation and the selection. Thanks. That's my presentation.
How many interactions did you go to? 2-level, 3-level, 4-level interactions between variables when you're building your tables?
Yeah, we have 2 levels, and we also have 3 levels: user, brand, and merchant.
Okay. And it seems like, I mean, if in the past I've done interaction tables, and then that greatly reduces the number of variables because then I don't have to have all the categories. I just have the average target rate. So what you were producing was just the existence of those interactions, yes or no?
I beg your pardon?
So in your interactions, the values of the interactions, that was just the presence of that user brand. Was that a binary value in the field, or was it an average of the target, like if they had bought before or not?
We generate numerical attributes. It's a count, not just a binary.
Okay.
And the value can be aggregated, such as average or standard deviation.
But the average or standard deviation was an average of the target, or it was an average of just the purchasing?
It can be the number of the purchase. It can also be the number of the click.
Okay.
And it can also be the number of adding to cart.
Okay, thank you.
Question back there.
Thanks. It was really impressive work. It was really good talk.
Thank you.
So I guess you're building for every every customer makes one purchase in this data set. It's their first purchase. And so you're building a customer level feature set. So I just wondered how you're incorporating merchant similarity into the model.
You mean like the merchant similarity?
Yeah.
So on the slide, you can see that in the training data, there's the user ID and the merchant ID, right? So, and we have a similarity matrix about the merchant similarity. We first apply PCA to reduce the similarity, or to reduce the dimensionality. And we only keep the 10 principal components. So each merchant will have a feature, or will have a factor with the 10 features. And by the merchant ID, we can join the factor with the training data by merchant ID.
I see. So you basically did a linear embedding of all of the merchants into the same space and use that as a feature.
Yeah.
Yeah,
Nice.
It sounds like it's more of a linear. You're putting in the latent space. You're not really computing the similarities between merchants and using that as features, from what I'm understanding.
You mean how to compute the similarity?
I mean, you don't actually compute a similarity between the merchants and put it as a feature, from what I'm understanding. You're just putting the actual vector from the PCA output into your data.
Yeah.
Is that correct?
Mm-hmm.
Chat more after. But, we had one more question.
Yeah, just want to ask, like, how do you do the model combining? You said you do the linear combining, but how do you choose the weights? What's the strategy or method you use?
For the weight, we tried many different ways.
Are you trying to
But
combine
finally,
all of the models, or
finally, we use we manually assign the weights to manually assign the weights. It's a linear combination of the probabilities of the single models and the weights are
So the
assigned
weights is
by
like
us manually.
the fixed weights for every observations?
Yeah, fixed by our experience. It turns out the manual assignment gives the best performance.
So you said there were 700 plus participants. Is that correct in the contest?
753.
700 out of 53. My question is, I mean, one thing deep learning is often sold as, marketed as, is you don't need to do extensive feature engineering, right? It can kind of figure out on its own. My guess is that depends heavily on the domain area as well as the amount of data. Did any of those entries use deep learning methods, and was there any evidence of that suspicion in the results?
We are not sure, but there are papers. I think that one team from MIT may use deep learning to generate features, but their performance or their score is not that high.
Interesting.
I think that feature engineering may still need some domain knowledge to generate meaningful features.
Right. How big was the data?
The number of
Sorry, I find this really
it
fascinating.
is more than 2 million.
2 million. Okay. All right.
Yeah.
One more question, and we'll go on to the next talk.
Yeah, for combining the model weights, you mentioned that you had fixed weights, but you tried other things. Was one of the things you tried building a model based on the model outputs of the submodels, like an ensemble?
Yeah, when we have the outputs of single models, we try different ways, such as we still use, for example, we still use GBM to learn the weights, and we also try the linear models. However, the results are not really good. Therefore, we just manually assign the weights to each model and combine them together.
But even then, it looked like your ensemble had only a very slight improvement over the
Yes,
best of the
actually,
individual models.
the difference between our score and the score of the second team is also fairly close.
So the ensemble pushed you over the edge.
Yeah, push us a bit over the second team.
Interesting. Interesting. Okay. Thank the speaker. Great talk.
Thank you.